What's up, everybody, and welcome back to another video from the Scalar Learning channel. This one is going to be amazing. It's an all-encompassing guide on how to use Desmos effectively, efficiently, and amazingly well on the digital SAT. So without further ado, let's do it. Before we get started, let's go over 3 general tips that I want you guys to always keep in mind. So number 1, when you're relying on Desmos, you must double check everything you type, because if you're gonna rely on Desmos and you make a typo, you're in big trouble. You're not gonna figure it out. So triple check everything that you type in. I said double check, we're gonna say triple check. Number 2, don't rush to use Desmos. Sometimes there's a really great way to do it algebraically or write it out, especially with geometry problems, sometimes even with discriminant related problems where you're trying to figure out is there no solution, 1 solution, or 2 solutions. Just plugging straight up into a discriminant inequality can often be more efficient than using Desmos along with the slider. Last but not least, if you are using trig functions, depending on whether or not you're using degrees or radians, you want to make sure you're in the right mode, and I'm going to show you how to fix that mode in a later slide. So now let's first talk about how to open Desmos in the Blue Book app. This is the most basic, but this is the first thing that you got to know in order to use Desmos. Otherwise, you can't find it. So here's a screenshot of the Blue Book app. The place where you're going to access the calculator is right here. You can see to the right of that, there's that reference button. So you can click that to access the reference sheet. So once you click that button, Desmos is going to open up like that. That's how you do it. Done. Now we're going to go over a number of keyboard shortcuts. Now, bear in mind, this is a Apple keyboard. So hopefully, if you do have an Apple device, this is going to make a lot of sense. For a PC, there might be some slight modifications, but let's go through all of these nice keyboard shortcuts. This is the most basic of basics. So to get the plus symbol, Shift plus. To get the minus symbol, you're simply going to hit minus, that minus button right there. To get the equal symbol, just hit that equal symbol straight up. Next, to get that multiplication symbol, we're going to hit Shift and the number 8. To get the division symbol, just that button right there with the question mark. And for exponents, you're going to hit Shift 6. For subscript, okay, and again, this was with the Mac, you're going to hit Command period. And sometimes you're going to need subscripts for particular advanced regression, which I'm going to show you later, but it's definitely less important than an exponent. And of course, for parentheses, you're going to hit Shift 9 for the left parenthesis, Shift 0 for that right parenthesis. When it comes to absolute value, you can type ABS parenthesis and enter the value that you want to apply absolute value to. But I always like to go with this method, just type Shift and that button right there, which is like that backward slash button. But when you hit Shift, you're going to get the straight up line, which is the absolute value symbol. And of course, you have to put that on both sides of the variable or the number. Now we're going to go through some keyboard shortcuts. Now, of course, this is for a square root of 7. So if you want to get the square root of anything, you type SQRT and then the square root will appear. Then you can put in whatever you want underneath the square root. For a cubic root or a 4th root, this is a trick that I like to remember, thinking about what is a cubic root. It is a rational exponent. So if it's like to the 4th root, you're raising it to the 1/4 power. If it's to the 3rd root, you're raising it to the 1/3 power. So if you simply type in 6, and then hit that exponent symbol and then type in the fraction 1/3, you've effectively got a cubic root. If we're trying to get percents, you can literally say, if you're trying to get 12% of 60, you can literally say 12% of 60. And you can also use this to solve for a missing percentage. Like if you're trying to find what percentage of 60 is equal to 30, you could say X percent of 60 is equal to 30, and it will spit out that X value for you. It's very powerful. If you want to get a table to render, just literally type in the word table. And when you do that, this is what's going to pop up. You can see in that little image down there, that is an X1, Y1 table. And last but not least, if you wanted to get a fraction to show up, you literally write 1 and then that division symbol, that slash symbol 3, and it will turn into a fraction. Now we're going to go through some quick tips. The first one is the export button. So this one is pretty cool. Let's say you have a function here and you want to export one of these points and you want to extrapolate it so then you can maybe use it or manipulate it or whatever. So you're going to click that little export button right there. I'm going to show you how to do that later on with equations as well. It's going to pop up over here and now you can use that point or that value, manipulate it however you like. There's also a fraction button. So for example, if you have a decimal value and you want to convert it to a fraction, or a decimal comes up as an answer and you want to see what's the fraction equivalent, you hit this little button right here that's going to show up automatically for a decimal that can be turned into a fraction. You're going to click that and boom, it gives you that fraction equivalent. And you can see it shows right here that it has been pressed. You also want to know how to access settings in case you want to adjust the window, if you want to go from degrees to radians or vice versa. So the place where you can go to settings is this little tool button right here in the upper right-hand corner. You click that and this will open up. So here you can see you can switch between radians and degrees. You can adjust the window as need be as well. Now we're going to move on to special operations, and this is a great catch-all for any function or any operation you want on Desmos. So check this out. If you have Desmos pop up like this and you see this button right here that says FUNCS, shorthand for functions, you click that and this opens up, and now you have access to trig functions. If you scroll down, you have access to all those stat functions, and you also have access to that nth root. So as I mentioned before, you can write something as a fractional exponent, or you can scroll down here and access that button right there. Now, for me, I like the fractional exponent option. I feel like it's faster, but this is a great option as well. Now we're going to talk about how to evaluate a value for a function, and it's pretty straightforward. The first thing you're going to do is you're literally going to write f of x or g of x or whatever the function is you want, right? So in this case, we're writing f of x equals 3x squared plus 7. So that's just a particular function. Then to find the function value when x is equal to 6, on the next line, you can simply enter f of 6 and it will spit out the value for you. So I'm going to show you how to use Desmos really effectively for a problem like this. So the first thing they're saying f of x is equal to x plus 6, and I'm going to write it in as I'm saying it, x plus 6, x plus 5, and x minus 4. So there's our function. It renders the graph. No big deal. Now, they also show a translation. Okay, so this is very interesting. Now, we can write the translation like they did, or we can spice it up a little bit. We can use a new function here and set that equal to f of x minus 3. So g of x is now f of x transformed down by 3. That's a vertical transformation, right? So we can just check there. Yep, it looks like it dropped it appropriately by subtracting 3. So that's pretty good. So now we got g of x. Now, I want to know which one of these tables is the right table, right? So I see, for example, g of negative 6, okay, because they're saying which table represents the y function, which is g. G of negative 6, which one will it be? Negative 9, negative 3, negative 3, or 3? Let's try it. So we're literally going to say g of negative 6. Boom. And it spits out my value of negative 3. So I already know I'm down to B or C. Now let's look at negative 5, right? Is it going to be negative 3 or negative 2? Let's type in g of negative 5. Look at that. It gives us negative 3. So this means that B, therefore, must be the answer. That's how you do it. Done. Now we're going to talk a little bit about transformations and how to represent that in function notation. Now you have an idea of how to write a function as g of x, f of x, whatnot. And once you have that, now you can apply transformations in the following way. So for example, if we want a horizontal shift, you're going to write f of x plus 2. Now this is left, right? If I go plus 1, plus 2, plus 3, it's all going to go to the left by those constant amounts. If I want to go to the right, if I want to go vertically up, I'm going to add plus 2, but I'm going to do it on the outside of the function. So in the previous slide, we saw f of x minus 3 that shifted the whole function down. F of x plus 2 shifts it up. We've also got horizontal to the right. That's going to be a minus, but within the parentheses. So x minus 2 is shifting it 2 to the right. X minus 3 shifting it 3 to the right. And of course, likewise, we have vertical down where we have the full function minus a value at the end outside of those parentheses. We can also apply a horizontal stretch, which is going to be less likely or less needed, I should say, on the digital SAT by putting in that nice fraction value next to the x. This is how you would do a vertical stretch, a nice value on the outside of the function greater than 1. And then for a horizontal compression, now we have a value greater than 1 next to that x. For a vertical compression, we're going to have a fraction outside of the function. Last but not least, we got our ways to do our reflections. That would be a negative on the inside. That's across the y-axis. A reflection across the x-axis would be a negative on the outside of that function. So for this question, it says the function is defined by f of x equals x minus 6, x minus 2, x plus 6 in the xy plane. And then it says g of x is the result of translating the graph 4 units up. What is the value of g of 0? So again, we're going to use the translation plus the evaluation on Desmos to get this nicely. So first, let's type in f of x. We got x minus 6, x minus 2, and x plus 6. So there's f of x. Then it says g of x is equal to f of x, right? When it says g of x is equal to y, and then y is equal to f of x up 4. It's just g of x is equal to f of x up by 4. And again, as I mentioned, translating up by 4, vertical shift up is going to be a +4 on the end. And then we can verify on the graph, did this appropriately translate this up? It's a little hard to see on the graph, but you can see, right, that point is at 135.2, this point is at 139.2. So it looks like we did that correctly. Now we're going to say, what is g of 0? Again, nice and easy. We just literally type that in. 76 is the winner. That's how you do it. Now let's talk about how to use this for linear equations. First of all, the beauty is you can literally type it in as is. You don't have to convert it to slope-intercept form. Standard form is fine, and it's going to render just like this. And when you click on those points, like I did in the image, you're going to get to see the coordinates. So right here, I can very easily find the y-intercept and the x-intercept straight up from the graph. And those intercepts are going to appear automatically, but the actual coordinate values, you'll have to click on it, but the points will be highlighted in gray automatically. Now you can use something like this, for example, to calculate slope. So one option to get slope from this equation would be to put it into slope-intercept form or get some coordinates. Or you can just look at those two coordinates, the x and the y, and say, okay, to go from one to the next, I'm going up by 4, I'm going across by 2. Since I know slope is rise over run, I know that my slope is going to be 4 over 2, which would reduce to 2. That's how you do it. Done. The graph shows the relationship between the number of shares of stock from company A, X, and the number of shares from company B, Y, that Simone can purchase. Which equation could represent this relationship? So we got a couple of ways that we could play around and solve this. Now, the first thing I could do is I can literally type in each one of these equations and see which one matches. And I got really good values here. I got a y-intercept and an x-intercept. So we need to match both of those points. We need to be hitting 60 here and 40 up here. So this is one option. Let's give it a shot. So we're going to start from the top and make our way down. Boom, that's totally off, right? We need something at, and I'll even put those points in, right? 0, 40, and we've got, what is that? 60, 0. So now we'll know if this line doesn't hit both of those points, we got a problem. Next, we got 8x plus 12y equals 480. Woo, look at that. We got a hit. So this is one way to do it. Now I'm going to show you another way to do this. We could do a little table, and we can put in both of those points. We could say 0, 40. And we're going to talk about regressions a little bit later. But this is another option. We get this, we get our little regression, and this gives us down here an equation of the line. Now, it's in slope-intercept form, but if you modify it to standard form, which is options B and D, that's another avenue to success. But again, these are both great options. Just wanted to show you both. That's how you do it. Now, when we talk about quadratics, once again, same thing. You can just enter the equation verbatim, and you can always click on whatever points you want to see the exact coordinates. But the beauty is that vertex is always going to appear automatically. In addition to the y-intercept and the x-intercepts, that vertex will show up. So if you ever need to find a vertex, just put it in whatever format it's in, click it, and you got it. The function g defined by f of x is equal to f of x plus 5. For what value of x does g of x reach its minimum? This is a quadratic translation hybrid. So check this out. We're going to first put everything in as is. And this is also a great little tip. If you're totally unsure of what to do, just type it in verbatim into Desmos and just see where that takes you. All right. So now we have the function. Let's go back to kind of our standard view. And then it says g of x is literally equal to f of x plus 5. So Desmos can interpret that and applies that shift to the left perfectly. And then it says, when does g of x, for what value of x does g of x reach its minimum? Again, you see that point, it highlights automatically. Click on it, and there's your answer. The answer is x equals -13. That's how you do it. Now, when we talk about systems of equations, there's a very nice order of operations that you can apply in Desmos to get to the answer nicely. So all you're going to do is you're going to enter both functions, right? You're going to find the intersection point, and that's going to be your solution. So right here, we entered them, you can see in this example, in standard form, didn't have to put it into slope-intercept form, and the intersection appears. We click on that, we get the solution, 6, 0, done. So for this question, we have a system of equations. I'm literally going to type it in just as is without modifying anything right here. Boom. We got the two systems. Now it says they have a solution. That's, again, my intersection point. We have to find that value of x. Now, I am double checking, making sure I didn't make any typos, but we're going to zoom out a little bit. And that's me just using the mouse to zoom in and out, which is pretty nice. You can also use these buttons if need be. And there's my intersection point. It's going to appear beautifully. Now, they said, what's the value of x? It's right there, 15. 15 is the winner. That's how you do it. Done. Inequalities, we have a similar idea. What are we doing? We're just going to enter the inequality and it's going to show up and it's going to render. Now, if you're unsure of how to put a less than or equal symbol, right? The less than is just that symbol, that little caret next to the M, and the one on the other side will go the other way. But if you want less than or equal to, you type that and then the equal symbol right after, and this pops up as less than or equal to. Same with greater than or equal to. You type the greater than, equal symbol, and boom, it auto-populates. And then you're going to have a shaded region. That shaded region will be your solution. So again, within inequality, you have infinite solutions, a whole region of solutions. Right here, that green shaded region, that's where you can get all your solutions. So technically, like this coordinate, 10, 0 is a solution to the inequality. We've got 5, 5. That's a solution to the inequality. So anyways, that's how you type in inequality. That's how you interpret it. Done. Now, with a system of inequalities, again, we have these first couple steps are the exact same thing, but now for the solution set, it's going to be the double shaded region. So in this example, we got 2 inequalities. We can see some of these coordinates here, but the solution set to the system is where we'd see the double shading, okay? So it's this really darker green area that's going to be my solution set. So again, 10, 5 would work. 5, 10 would work. Now this down here, which would be 5, -5, that would not work, right? That's just a single shaded region, not a double shaded region. Now we come to circles, and again with circles, no surprise here. We just enter the circle equation as is, whether it's in this format or regular standard form. And then the most important thing to remember is the exact top and bottom automatically appear. You may have to click them to get the coordinates to show up, but this will always show up. Why is that valuable? Because you can use those to calculate the radius. So if you're familiar with this format, I know the radius is going to be the square root of 16. It's going to be the square root of that r squared value. But if you don't know that, this is amazing because I'm literally taking the distance between these two y values, right? 9 to 1, that's a distance of 8. And that's the diameter. To get the radius, we divide it by 2, we got a radius of 4. So that's how you can use the graph effectively to figure out those important characteristics of a circle. The other thing is, if you want to find the center, it's also the midpoint of that top and bottom point. What is the diameter of the circle in the xy plane with this equation? So let's go ahead and enter it. We got x minus 5 squared plus y minus 3 squared is equal to 16. And again, now we're going to zoom out and we're going to look at the circle. So I know that my radius is the square root of 16, which is 4. And I know the diameter is double that, which is 8. So I know that because I know the equation of the line. But if I don't know that, I just click here and here. And check it out. I've got 7 on the top, -1 on the bottom. So the diameter is that full distance between -1 and 7. 7 minus -1 is 8. Double verified. That's how you do it. Done. Now we're going to get into something very, very important. Regressions, and Desmos has made it very easy to do regressions. So check this out. You're going to first type the word table. Now, of course, you could use that little click button, plus button to get a table as well, but I just usually write table and the table will populate. Once that happens, you enter the points that are given in a question. You need 2 points only for a line. 2 points only for an exponential in a times b to the x format, like a traditional exponential. For a quadratic, though, that's not going to cut it. 2 is not going to be enough. You need 3 points to generate an accurate quadratic regression, okay? So now and then you're going to click the regression symbol. So what does this look like in Desmos? Here's Desmos. Here we entered all of our points. We got 3 points. This is going to be a linear regression, just as an example. So you're going to click this button right here, and boom, you got a linear regression. It's beautiful. Now, if you want to extract this equation down so you can manipulate it or plug things in, you click this button right here, and then it's going to pop up right there. So now you got the equation. Now you can manipulate it as need be. Also, if you want to use a different type of regression, if linear is not the right one and you want to try something else, you click this drop-down button. You can do linear, quadratic, or exponential, whatever you want. Those are the 3 most likely to be used: linear, quadratic, and exponential. There's a chance there might be another one on the SAT that's relevant, but those are the 3 that are most commonly tested. So for this one, we're going to use a combination of a regression, and then we're going to also use some nice transformations. So check this out. We got 18, 130, we've got 23, 160, and we've got 26, 178. So we've got all of this, and now this says 3 values in the x corresponding y values. This is a line. So we're going to use our nice linear regression, and we got our linear equation, right? I just extracted it. Now we've got y equals 6x plus 22. Great. Then it says line K is the result of translating this down 5 units. So watch what I'm going to do. I'm going to take this extracted function. I'm going to call it f of x. Then I'm going to say g of x is equal to f of x minus 5. So we already know that is how we get a vertical shift down. We can quickly check it, right? We can see at this particular x value, negative 2.8. We have 5.2 at negative 2.8. There we go. We have 0.2 that went down exactly by 5. So we know we've done it correctly. Then it says, what is the x-intercept of line K? I mean, this is just so beautiful. It's right there. Negative 2.83 repeating. Now, unfortunately, this is a decimal. It's not a fraction, and that's how they present it here. And I can't turn it into a fraction with that fraction button because it's basically been cut off, right? It's been rounded. But that's obviously a repeating decimal. Well, that's not so bad. We can still figure this out by trying all the answer choices. So I can first type in negative 26 thirds. Nope, that didn't work. Maybe let's try 11 thirds. Nope, that didn't work. Maybe let's try 17/6. Look at that. Right on the money, negative 2.83 repeating. That's how you do it. Done. Now we're going to talk about advanced regressions. Now take this with a grain of salt because I'm always going to say that this is going to be the most efficient method possible, but I want to show it to you for those of you guys who are looking for regression analysis for more complex functions or out of those general, basically the general formats that are provided with the auto regression feature. So this is how you can do a fancy regression, an advanced regression. So again, you're going to type table, you're going to enter your points, no big deal. All of those are going to be the same. Then you're going to enter this in a number line. Y sub 1 is approximately equal. That's right beneath the escape button, that little squiggly symbol. mx1 plus b, and this is for a linear function. So if you look right here, this is an example. And the reason why we have to use y1 and x1 is because that's what's in the table. And then you put in the constants of m and b. And what it does is it will automatically generate the correct slope and y-intercept value for you. So in this one, we've got ax plus b. That's the exponential. And again, that is not what Desmos is programmed for. Desmos is programmed for a times b to the x. So that's why we can't use the standard boilerplate regression that is embedded within that little regression function. So we're going to have to do something a little bit different. But we're going to start the exact same way. We got table. We got two values, right? We've got 0, negative 25, and we've got 2, 23. Those are the only two values we have. And then we're supposed to find a and b, and they said, what is the value of a and a plus b? Now, again, just to show you, if I did the regression, okay, let's press this button here, you're going to see for exponential, again, it gives me a times b to the x. That's not what we want, okay? So we're going to turn this off, and we're going to go back to the table. So now I'm going to show you how to do this. Again, we want y. Now to get that subscript, I'm hitting command, period, and we got a 1. Then we do my little squiggly symbol is equal to, and they want a to the, now we're going to do shift 6, and we're getting up here x, again, command, period, and we're getting that little 1 down there, plus b. And that's it. It's as simple as that. I mirrored the format that they wanted, and I get my a value, my b value. Then what does it say? What's a plus b? 7 plus negative 26 is negative 19. That's how you do it. Done. Now, this one's really crazy. You really got to read between the lines to actually utilize a regression successfully here, but I'm going to show you how to do it in case you want to see it. I do also think this one is great by hand, but let me just show you. So again, we've got a table of values for g of x. So we've got negative 27, 3, we've got negative 9, 0, and we got 21, 5. So we got these great values. And what is this for, right? This is for g of x. And what is g of x? It's equal to f of x, which is linear. That's very important, over x plus 3. So how are we going to use this? Well, I'm going to, again, set it up. We got y1, which represents g of x, okay, is equal to, now here's the interesting part. They've got f of x, right? But I don't want to throw another function in the mix. That's not going to provide the results that I want. Instead, they said that f of x is linear. Well, wait a minute. Can I represent a linear function as mx plus b, right? So we've got this. And by the way, see, I forgot. I accidentally typed equal as a habit. You got to type in the squiggly. Otherwise, it's not going to work. mx plus b, that's my linear function. That's my representation of f over the same x. And then we've got plus 3. Look at this. Look at this. Look how fast that is. By recognizing that that's linear and by plugging this in, it spits out my m value, which is that value, and my b value, which is 36. And what do they want to know? They want to know the y-intercept, which is my b value of a linear function. My answer is 36. A is the winner. Done. Now we're going to talk about using sliders. I'm going to show you an example as well on how to do this. But the main idea is, look, if you're trying to find a constant, just enter the function with the constant, whether it's c, whether it's b, whether it's k, whatnot. Then you're going to click Add Slider and then adjust that slider. You're going to slide it around until you get the desired result, depending on the question. So as an example here, I typed in y equals 3x squared plus 7x plus c, and it even prompts me. It says add a slider. You click that button right there. You click that little c, and boom, it shows up. And then you can slide it left and right and modify it. And here's an example where I slid it up to 4 and it slightly modified the function. So right here, we've got negative x squared plus 9x minus 100. So that's my function. You don't even need the y, but I'll just put it in anyways. Y equals this, okay? So now we've got our function right here. You can see it's a little parabola like that. And it says, it intersects the line y equals c at exactly what point? What is the value of c? So you notice when I type in y equals c, I actually get this weird line. And sometimes Desmos does this. I don't know why, but it treats it as a variable. But even though the c slider button didn't highlight like that option, you can still type in c equals 4, just as an example. And now a slider is going to show up. So again, we want to say it intersects at exactly 1 point. So if you're not even sure what it's asking, let's just play around with this. Let's move it down. Okay. And then it didn't go down far enough. Now you might say, oh, I'm stuck at negative 10. What do I do? You can modify the bottom value to be negative 100, let's say, right? Or negative even, 200, depending on how far you think you need to go down. So now you can really start to see we can get some movement here. And we want it to intersect at exactly 1 point. You want to be very careful here to zoom in and make sure it's hitting it exactly once, right? So I go to negative 80. Oh, it went too far. Negative 79. That's not, or negative, there it is, 78. It's not enough. So we got to go somewhere else. Now we can start to tweak it, okay? So we can say 79.5, 0.6, 0.7, 0.75. And I believe that's going to be right on the money. And there's the confirmation, right? You would see 2 dots if you went too far. So let's say we went to 8. Now you're going to see, right, 2 dots showing up, 1 and 2. But that's not what we want. We want just 1 point of intersection, which again is at the 0.75 mark. And the value of c is right here, negative 79.75. So we're going to turn this into, let's see, an improper. Maybe let's see if this works here. So we're going to do this. We're going to go bop. And there's our answer, negative 319 over 4. C is the winner. Done. So in this one, we got a function with ax plus b. A and b are constants. Now, we're going to type it in as is, right? We're going to say f of x equals a square root, right? You saw me type sqrt. X plus b. And we need sliders for both of these. So I'm going to click that all button. Now, we're going to use sliders to figure out what these values are based on what they gave us. So first of all, they said it has to go through the point negative 24, 0. And they're also saying that f of 24 has to be negative. So what is f of 24? That's the function value at 24. So right now you can see it's positive. So it's like you can say, well, what do we need to manipulate to change that around? If I manipulate b, I can see I'm just moving it left and right. This, as it gets bigger, it goes up, but as it goes negative, now I flip down, and now my value at 24, is a negative value. So I know A has to be negative in this case. And then what about B, by the way? So to figure out B, well, you already saw that B moved it left and right. And now you can tell the only way, right? There's no way that we can shift it up or down. To get negative 24, 0, we're going to have to modify B. And so now you can play around with it. Still, it didn't hit negative 24, 0. And then you're going to find out that when B is 24, boom, that's how you get to that exact point. So again, this is a way that you can play with the sliders to sort of figure out at least where these values roughly have to be. We found for B that it has to be exactly 24. For A, we just know it has to be negative. Now we're going to talk about data sets, mean, median, and beyond. So this is a great way that you can leverage Desmos as well. Now, if you're trying to calculate the mean of a data set, you just literally say mean, and then you put in the data set with commas. You don't even need a space. 1, 3, 7, 8. You can do the same thing with median, just like that. You can do the same thing with standard deviation. You can just type STD, DEV, and all that. Now, Just a quick caveat, I'm telling you that, but you don't really need to ever calculate standard deviation. You just need to understand it, and you understand that the greater the spread of the data away from the center, the greater the standard deviation. The more compact it is around the center, the smaller. But if you forget that, you can calculate the actual value of standard deviation. And the other thing is you can store a list. This is really beneficial as well, because when you store a list of data, then you can perform these various operations by just typing mean of L, median of L, standard deviation of L, etc. So in this example here, there is my L list with those brackets 1, 3, 7, 8, and you can see I did median, mean, and STD, DEV, or standard deviation, and it calculates them for all. So for this one, we have two data sets, and we're trying to compare the mean of data set X and the mean of data set Y. So I'm going to show you how we're going to do this with, I'm going to store this into two lists. So we're going to say M is equal to, or let's say X actually. I'll see if that works with the capital X. X is equal to 5, 9, 9, 13. And then we're going to say down here, we'll say Y is equal to 5, 9, 9, 13, and 27. Boom. And now we're going to get the mean of both. So let's see the mean of X and the mean of Y. Very nice. So we got the means of both. Of course, the mean of Y is bigger, so the mean of dataset X is less than Y, and that's how you do it. Now, I want to say you could do this without using Desmos very easily. Hopefully, if you recognize that the numbers are the same, but for an extra really big number, you know that Y has to be bigger. But functionally, this is how you would use Desmos in real time. That's how you do it. Done. All right, guys, that is it for the Desmos Bible for SAT Math, the complete guide. I hope you guys enjoyed it. If you did, please click that like button. And if you want to see more from the Scalar Learning channel, make sure to click subscribe. If you're taking the digital SAT, I wish you the best of luck, and I will see you guys in the next video. Take it easy.